Okay, so I'm going to lecture on 1210 this morning, and as I tried to figure out exactly what I was going to say, I went through the homework problems that I assigned, and there were a couple of homework problems that I think just maybe were slightly trickier than I wanted to expose you to. So I'm crossing 39 and 41 out of the homework. Had planned on doing 39 and 41 when I did my video, but they have just tricks in them that maybe the author didn't really prepare you for. So you can skip those problems and they won't make their way onto the test. Section 1210 is a section that asks probability questions, and every single problem, because it's a probability question, I'm going to form a fraction to get my answer, and the author has worded the problem so that every single computation can be done with combinations, and I won't have to use the counting principle. I won't have to list sample spaces. So every problem in section 1210, I'm just going to do fractions where that has combinations in the numerator and combinations in the denominator. I put a handful of problems on this video that are kind of extensions of the author's problems, just to help you have a resource when you're doing the take-home test. So hopefully this is going to be helpful as a resource when you go to do the take-home test. This section are these kinds of problems, probability questions with combinations. The most harmless questions can get incredibly tricky and difficult. So I tried to really focus the problems that I did to just kind of the standard combination problems. So when I skipped over 39 and 41, it's because if you read the problems, you wouldn't think they have any horrible tricks to them, but they have some subtleties in them. 39 has the word at least, and at least starts the beginning of opening up a really difficult area of probability with combinations. So I'm just focusing on what I think you'll need for the take-home test and what seems sufficient to learn in Math 142. So part of the reason I do section the chapter 12, decide to do chapter 12 in two parts, is because some of the problems at the beginning of the chapter in the first 6 sections and some of the problems at the end of the chapter, they can be done in more than one way, and generally, having multiple ways to do a problem is not, a good thing, in that you start to get confused as to which way should be used or which way is better to use. And this problem 1 in section 1210, it's not inconceivable that you could do this particular problem by creating a sample space and using the sample space to answer your probability questions. But I won't do any sample spaces for any of the problems in 1210. All of the problems in 1210, the author worded carefully enough so that combinations are going to be appropriate. So immediately when I see determine the probability, which I'll see in every one of these problems, I know that my answer is going to contain a fraction. When you watch the 12.9 video, there were no questions in 12.9 that asked the question, what is the probability? All of the questions in section 12.9 ask the question, how many? And how many questions you don't use fractions to answer. So there weren't any fractions in my answers to section 12.9. All right, so let me just get started. So in problem 1, a bag contains 6 blue and 10 red balls for a total of 10 balls that are totaled in that bag, 6 red and 4 blue. It says 4 balls are to be selected at random. Determine the probability that all are red balls. And I'm going to form a fraction. The numerator of the fraction is going to be the number of items in the sample space that has the look that I want. And what I want is I want 4 red balls. The denominator is the number of items that are possible without restrictions in the sample space. Part of the difficulty in the problems in section 12.10 is that not all the numbers that you need for the problem are always given in the problem, and that's the case here. I snuck an extra number in that I knew I was going to need. And hopefully as I do enough problems, you'll start to get an idea of what extra number, if any extra numbers, need to be computed before you get into the problem. So in the numerator, I'm going to find the number of items in the sample space that have red balls. In this particular problem, I'm selecting 4 balls, and in the numerator, I want 4 of them to be red, and that combination that gets that, from the 6 red balls, I want to pick 4. So in the numerator, I'm going to form a combination to get the look that I'm looking for, and I want to get, I know I want to get, this is a number that I need, and that goes to the left or to the right of the C. So I need 4 red balls, and to the left of the C, I put what I have, and I have 6. In the denominator, I need to get 4 balls, so I'm going to put that to the right of the C, and what I have, the denominator is what you could get, and you can get any of the 10 balls. So the combinations in the denominator is what could possibly happen. I can get any 4 of the 10 balls. The numerator is specifically what I want. I want 4 of the 6 reds. Now I'm going to compute each probability separately. In the numerator, I do a 6, and then my math key, and then I'll arrow over to PRB, down to number 3, and type the number 4, and I'll get 15. The denominator, I'll type the number 10. I'll hit my math key. I'll arrow to PRB and down to number 3, type the number 4, and I get 15 over 210. Now I'm going to reduce this fraction. I'm going to go 15 divided by 210 equals math, enter, enter, and my calculator tells me that the probability of getting 4 red balls is 1 in 14. On the test, it could be the case that I could ask you a slightly more complicated question, and so I put this problem down at the bottom of this sheet. So this still relates to problem 1, where I'm still selecting 4 balls from the 10 balls, but instead of only wanting 1 color of ball, I decided I wanted 2 colors of balls. And in the numerator, I need to separate the look that I want. So in the numerator, I want both red and blue balls. And I'm going to make a combination for each. And I'm going to separate the combination by a times sign. For the red balls, I want 3 of them. For the blue balls, I want 1 of them. And to the left of the combinations in the numerator are the number of red balls and blue balls that you have. So there's going to be 6 red balls and 4 blue balls that I can choose from. So to get the setup, this part of problem 1 set up, if I want specific more than 1 kind of ball, then I need to have a combination for each thing that I'm picking. I wanted to get 3 of the 6 red ones and 1 of the 4 blue ones. The denominator, I could get 4 of any of the 10. Let me compute each of the combinations separately. The denominator I don't have to do again. It's the same 210 that I did in part 1. For the numerator, I'll do 6 math. I arrow backwards to get to the PRB quicker. And the first thing, the 6 choose 3, comes out to be 20. And then when I do 4 choose 1, I think it's just 4 math. So this is going to give me 20 times 4, which is 80, over 210. I can reduce that without my calculator. The answer to this additional part of number 1 is going to be 8 over 21. Just canceled out the zeros there. Okay. Most of the problems that we're going to do kind of fit this mold perfectly. Either I'm going to have one combination over one combination, or I'm going to have two combinations over one combination. The denominator for every probability question in section 12.10 is just going to contain one combination. The numerator could have more than one combination if I have more than one type of object that I'm looking for. So the next problem I said I'd do was number 2. So number 2, a class has 19 girls and 15 boys. That's a total of 34 students. This is a number that's not given in the problem that I'm going to need to back into. And it says 12 of the students are to be selected at random. Determine the probability that they're all girls. I'm going to form a fraction. The numerator is going to contain a combination that allows me to get 12 girls. And the denominators is going to be a combination of what could happen. In the denominator, I want to pick 12 students. 12 is going to go to the right of the C. And to the left of the C is the total number of students I have to choose from. In this case, I have 34 students to choose from. In the numerator, I make the look that I want. I want to have 12 girls, and I have 19 girls to choose from. So to the right of the C is the number that you want. To the left is the number that you have. So I want 12 girls of the 19 girls. The numerator is what you want to get. The denominator is what you can get. I can get 12 of the 34 students. I'm going to do each of these C's separately. So go 19 math, C 12. And get a big number, 50,388. And then the denominator is going to be unfortunately larger. When I do 34 math, C12, it's going to be way bigger, probably too big for me. So 54, 8, 3, 5, 4, 0, 4, 0. Now I'm going to divide these. And when I divide these, my calculator probably won't be able to reduce the fraction. On the take-home test, when you get the fraction that needs to be reduced, if your calculator can't reduce the fraction, just give me a decimal, 3 decimals worth of accuracy. So when I do this 5388 divided by 548354040, and I hit math, enter, enter, my calculator can't make that into a decimal or fraction. And my calculator gives me this, 9.18889.5, which is a bunch of stuff, and an e to the negative 5. An e to the negative 5 is my calculator's way of telling me to move the decimal 5 places to the left. Negative means left. So I'm going to take this decimal, I'm going to move it 1, 2, 3, 4, 5 places to the left, and I'm going to fill zeros in the spots where there aren't numbers. And my calculator tells me that this really is 0.0000918895. And I said to round to 3 decimal places. Well, 3 decimal places would give me like a 0%. I'm gonna go up to the 9. So I'm gonna go up to the first non-zero number when I can't. When my rounding of 3 decimal places would just be zeros. But if you gave me that whole string, I'm completely fine with that. I didn't write a 0 to the left of any of the decimals. It wouldn't have been wrong to do that, so I could have also written 0.000009. I don't think I want an answer that just has all zeros in it, so the fact that I said round to 3 decimals and my answer doesn't have 3 decimals is specifically because I didn't want to see at least a number in the answer. So I threw down an extra problem. The extra problem gives a more specific look or a harder look to compute. The denominator, still the same problem, so I still can get any 12 of the 34 students. The numerator wants me to get 8 boys and 4 girls. For the boys, I'm going to make a combination for them, and to the right of the C for the boys, I'm going to write an 8 because I want 8 boys. For the girls, I'm going to make a combination for them, and to the right of their C, I'm going to put 4 because I want 4 girls. To the left of the combinations are the number of boys and girls that I have. So for the boys, I want to get 8 of the 15 boys. For the girls, I want to get 4 of the 19 girls. In this case, you can see the 34. The 34 is the 15 and the 19. And you can see the 12, which is the 8 and the 4. Let me do those combinations. 15 math, 8. I get 6435. And then 19.4. I get 38.76. I'm going to do this whole combination, or this whole fraction at one time. I'm going to go parentheses 6435 times 38.76 to close my parentheses to give my numerator, then divide it by 548354040, and then math, enter, enter. My calculator can't reduce this, so I'm just going to give 3 decimals worth of accuracy. There's no e's, so I don't need to move my decimal. And I write 0.045, and that's 3 decimals. The number after the 5 was a 4, so the 5 didn't need to be rounded up to a 6. You could have written a 0 to the left of the decimal and write 0.045. So the difference between the problem 2 that the author gave me and the problem 2 that I added to is the author only wanted 1 sex, so I only needed 1 combination in the numerator. I wanted both sexes, so I need 2 combinations in the numerator. The denominators doesn't change regardless of how the mix of boys and girls that I'm looking for. So 4 requires me to know something about a deck of cards, and card problems I think are inherently the hardest because once you're familiar with since you're familiar with cards, it's tempting to want to put numbers in the probability that you're familiar with that don't belong there. So in the numerator, I'm just looking for getting 3 aces when I'm being dealt 3 cards. So in the numerator, I'm going to make a combination for what I want to get. I want to get aces. And in the denominator, I'm going to make a combination for what I can get. So I'm being dealt 3 cards from a standard deck. We have to know that a standard deck of cards has 52 cards. What I could get, the denominator, I could get 3 cards of any of the 52 cards. So the denominator is what could happen. The numerator is what I want to happen. I want to get 3 aces. So to the right of the C in the numerator for the 3 aces, I'm going to put a 3. To the left, I'm not going to put a 52. To the left, I'm going to put the number of aces that are in a deck of cards, just like in the last numerators. I put the number of girls or the number of boys to the left of their combinations. For this particular numerator, I'm going to put the number of aces to the left of the combination for the aces. This is going to be another E problem, I think, on my calculator. So when I do 4 choose 3, I get 4. When I do 52 choose 3, I get 22,100. Even though I could reduce this probably quite nicely, I'm going to make my calculator do it. 4 divided by 22,100. Math, enter, enter. Oh, my calculator actually was able to reduce that because I could reduce it, it could do it. So I'm always going to attempt to give a fraction answer. If my calculator can't make the decimal into a fraction, I'll give the decimal answer, round to 3 decimals, unless those 3 decimals have just zeros in them, and then I'll go till I get a number. So I made an extra problem to help when you do the take-home test. You notice my work didn't have a 5 in it anywhere. A lot of times when you're being dealt cards, you're being dealt 5 cards, but in this case I'm being dealt 3 cards, so 5 wasn't appropriate. So to extend this problem, regardless of what combination of cards I want, the denominator is going to be 52 choose 3 because I could get any 3 of the 52 cards. The numerator, This particular problem says I want to have 2 aces and 1 king. So because I want 2 different cards as opposed to just 1 card, I make 2 combinations in the numerator. To the right of the aces, I put a 2 because I want 2 aces. To the right of the king, I put 1 because I want 1 king. To the left of each of the C's, I put the number of that kind of card in the deck. And because there's 4 aces in a deck and 4 kings in a deck, to the left of each C, I put a 4. The combination for my denominator, because it's the same as the top part, I put 22,100 for the number that equals that. 52 choose 3. And then 4 choose 2 I can do in my head, but I don't want to try to be impressive. So 4 choose 2 is 6. 4 choose 1 is going to be 4. So this is going to be 6 times 4 over 22,100. I'll do this again on my calculator. I'll go 6 times 4 in parentheses, divided by 22,100, and then math, enter, enter. And the answer that I'd write here is going to be 6 over 5525. And I will only give a decimal answer if my calculator can't give me a fraction answer. Six is another combination over combination problem. There's 80 people at a dance, 28 have a college degree, the other 52 don't have a college degree. 4 people are selected at random. Find the probability that all have a college degree. I'm going to do a combination in the numerator, a combination in the denominator. In the denominator, there's 80 people and I'm selecting 4. So the 4 in the denominator is the total number of people I'm selecting. The 80 is the number of people that I'm selecting from. In the numerator, I want all 4 to have a college degree. To the right of, I only need 1 C in the numerator because I'm only having one kind of person. I'm not picking people with and without college degrees. To the right of the C is the number of people with college degrees that I want. I want 4. To the left of the C in the numerator is the number of people that I have to choose from, which is a 28. So if I do 28 math 4, I get 20,475 for the top, and then the 80C4 is going to be a really large number. It's 1,581,580. I could reduce this by 5, but I won't. I'll let my calculator reduce, and whatever it tells me, I'm going to live with that. Oh, my calculator could also reduce it. I guess if I can intuitively reduce it, my calculator also can. So for an answer to number 6, I'm going to write 45 over 3476. 9 through 18, those problems are really problems that would have lent themselves nicely to listing a sample space and doing the probabilities just by picking items from the sample space, much like we did probably in section 12.5. The author has a little write-up at the beginning of problems 9 through 18, and so these are problems that are without replacement. And then I parenthetically said in order doesn't matter, even though the author didn't say that, he implied that. And that little wording at the beginning before problems 9 through 18 tells me that each of the problems between 9 through 18 can be solved with combinations. And very specifically in the instructions, the author says use combinations to determine the probability. So I'm going to read through the problem, and every single problem in section 12.10, the denominator is going to contain one combination. What it's going to contain to the left of the combination are the number of items I can get. To the right of the combination is the number that I'm selecting. So in problem 10, the numbers 1 through 6 are written on a piece of paper, placed in a hat. 2 numbers are selected at random. Find the probability that both numbers are even. So in the denominator, I want to get 2 numbers. I can get any of 6, so that's a 6 choose 2. In the numerator, I'm not looking for two kinds of numbers. I'm only looking for even numbers. So in the numerator, I don't need two C's because I'm only asking for even numbers. The combination I'm going to have in the numerator is the number of even numbers I want. I want to get two even numbers. And the number of even numbers I have to choose from is 3, the numbers 2, 4, and 6. That's going to go to the right of my combination. So it's going to be a 3 choose 2 in the numerator. 3 choose 2 is 3. 6 choose 2 is 15. And that's a non-reducible fraction. So the answer to number 10 is just the probability of getting two even ones when you're doing that is 3 and 15. You absolutely could have listed the sample space and gotten that answer without doing combinations. Even though the author told me to do combinations, the sample space would be small enough. I could have done it like I did that kind of problem earlier in the chapter. Well, I know we had a problem earlier in the chapter that talked about a guy's wallet, or a wallet with bills in it, and that problem we listed a sample space and then we used the sample space to compute probabilities. Could do that again, but I don't have to. So Duck, gosh, is that in the, forget it, in the movie Pretty in Pink there's a guy named Duck, and I don't know why that makes me think of that, but has absolutely nothing to do with this. So anyways, Duck has 8 bills in his wallet, and he's going to take 2 bills out of his wallet. I want the probability that they're both 5s. I'm going to form combination over combination. In the denominator, it's what could happen. I could get 2 bills of the 8 bills Duck has in his wallet. The numerator is what I want, and I only need 1 C in the numerator because I'm only wanting one denomination of bill. I need to get 2 $5 bills. To the right of the C for the $5 bill, I put the 2 $5 bills that I want. To the left of the C, I put the 4 $5 bills that I have. So it's going to be a 4 choose 2 over an 8 choose 2, which of course we know is 6 over 28. Let me make sure I didn't mess those up. So 4 math probability 2, there's the 6, 8 math probability 2, there's the 28. 6 over 28 I can reduce without my calculator, but because I have it handy, I'll do the reduction with my calculator, and I get 3 and 14. Absolutely could have done that problem by listing a sample space, but it was quicker to do it with combinations. The next problem seems like the kind of problem I would have asked on the test, so I made up an extra part to it. So a committee, almost all the time that we have committee problems are combination problems. Every problem in this section's a combination problem, so I'll make a combination in the denominator of my fraction. The denominator is going to be what could happen. So I'm going to make a committee of 4 from a group of 7 teachers and 8 students. Find the probability the committee will consist of 4 students. So in my denominator, what could happen, I'm picking 4 people of the 15 people, 7 teachers and 8 students. So what could happen is I could select randomly any 4 of the 15 people. The numerator is the look that I want. I want to have 4 students. I only need 1 C because there's only one kind of person that I want of the 8 students. So 8 choose 4. I want 4 of the 8 students. And I could get any 4 of 15 students or 15 people. So I get 70 over 1365, and that fraction reduces to 2 over 39. I made an extension to this because I thought this extension would help on the test. I'm still selecting 4 people from those 15. But now my look says I want one teacher and 3 students because I want 2 different types of people. I'm going to make 2 combinations, one for the teacher, and I want to get 1 of the 7 teachers and 3 of the 8 students. So the combination problem is going to be 7 choose 1 times 8 choose 3. I needed 2 combinations in the numerator because I needed both teachers and students, whereas the original problem 16 only asked for students, so I only needed 1 combination in the numerator. In the denominator, it's still the 15 choose 4. And then you can do each of the combinations on your calculator. And once I get the numbers for the numerator, I'll multiply them in a parentheses and then divide and then reduce the fraction. And my calculator says the probability of getting 1 teacher and 3 students is 56 over 195. So hopefully you're starting to kind of predict what I'm going to do. It would be nice if for the last 5 problems or so that I'm going to do, if you could try to do the problems without the video playing and then just put the video back on to check yourself. Ultimately, if you can do that, then you're doing well. So 24 is almost too tricky, but I didn't think it was, so I left it on there. So a particular baseball team has 10 pitchers, 6 infielders, and 9 other players. If I add the number of players on the baseball team, 10 plus 6 is 16, and 9 is 25. So this baseball team has 25 players. We're going to select 3 players' names randomly, and I want to determine that the probability that none of the 3 is a pitcher. I'm going to form a combination. In the denominator, I'm picking 3 names randomly from the 25 names. And in the numerator, I want none of the 3 to be a pitcher. What I'm going to do for the numerator is I'm going to group the 6 infielders and 9 other players into one group of 15. And I'm going to call that the 15 non-pitchers. And I want to get 3 of those 15 non-pitchers. I don't care if I happen to get like 2 infielders and 1 other player, or 3 other players, or 2 other players and 1 infielder. That doesn't matter. In this case, the 6 infielders and the 9 other players, I'm just calling those non-pitchers, and that's what I want. I want none of those 3 to be pitchers, so I want to get 3 of the 15 players that aren't pitchers. And so in this case, that's why I said maybe it's a little bit tricky, because I had to group the players that weren't pitchers together into a group of non-pitchers. And when I do this, I get 15 choose 3, which is 455, over 25 choose 3, which is 2300. Find the fraction and reduce it, and the author would give us a 91 over 460 for the answer. 26 is the kinds of problems that I added for my extensions when I extended some of the first few problems. So in 26, I could, when I'm selecting 3 names, get any 3 of 25, but I want to have 1 pitcher and 2 other than pitchers and infielders, and there are 10 pitchers to choose from, and players other. That second combination, I'm assuming that the author wants those 9 people. Those are the 9 that are considered other than pitchers and infielders. So I needed 2 combinations in problem 26 because I'm looking for 2 types of players, 1 pitcher and 2 others. And when I do the combinations, the new 10 choose 1 you could do on your calculator, it comes out to be 10. The 9 choose 2 comes out to be 36, and the denominator comes out to be 2300. Let me make sure I haven't messed up my combinations. 10 choose 1 is easy, but 10 math choose 1, I get 10, and then 9 math, choose 2, I get 36, and now I'm going to go 10 times 36 in a parentheses, divided by 2300, math, enter, enter, and my calculator says this is 18 over 115 would be the probability of getting one pitcher and 2 other players. (27 through 30) is a jury problem, and there's either a jury problem on the extra practice problems I'm going to pass out for this chapter or on the test itself. And the nice thing about these jury problems is the author forced both of my numerators to have 2 combinations. So a jury has 17 men and 22 women, which is a total of 39 people. So the 17 men and 22 women, which are in a jury pool, are going to be interviewed, and they're going to pick 12 for the jury. It's definitely not the case that jury pools are random, because you're interviewed and you're thrown out for a variety of reasons. But this basically problem says I'm randomly from these 39 people going to pick 12 jurors. What's the probability that the jury pool, the jury has the look that I want? So the denominator, if I'm randomly picking from these 39 people, if I'm randomly selecting 12 of them, the denominator for the probability is going to be a 39 choose 12, because I could pick 12 of the 39 people, but I want to get 8 women and 4 men. So I'm going to make in the numerator 2 combinations as opposed to 1. 1 for the 8 women, and there's 22 women to choose from, so I'm going to get a 22 8 for that portion of the numerator. And I want to get 4 men, and I get a 17 4 for that portion of the numerator. These numbers are going to be really big, and it's going to be a nuisance to write these even. (22 choose 8 is 319,770. 17 choose 4 is 2,380. And then down low, it's going to be a really large number. 39 choose 12 is 39107974336. Let me do this multiplication. Go 319770 times 2380, and then divide by 39107974336. I suspect that my answer is going to come out as a decimal that my calculator can't make into a fraction, but maybe it can. It can't. So I'm just going to round to 3 decimal places for my answer. I'm going to write 0.19 and not write that 4, because the number after the 4 is a 6, so I'm going to write 0.195 or 0.0195 if I care to. 29, same style of question, so I could get any 12 of the 39 people in the jury pool, but I want 6 women, so I can get 6 of the 22 women and 6 men, and I can get 6 of the 17 men. Yuck. So here, when I do 22 choose 6, y'all. When I do 22 choose 6, I get 74,613, and then 17 choose 6 is 12,376, and I'm going to do 74,613 times 12,376 divided by that number again, because the denominator is the same. So divided by 39107974336. Calculator gives me 0.236. Try to round it or make a fraction of it. It's too big for my calculator. So I'm not going to give a fraction answer when my calculator can't do the reduction for me. And to 3 decimal places, the third decimal place is a 6. After that's a 1, so I don't need to round the 6 up. So for an answer, I'm going to write 0.236 or 0.236. So you ultimately don't have to be the the king of the world in combinations. If you can just kind of, as you're going through the take-home test, kind of match the take-home problems up to the video problems, you should be able to do well on the take-home test without maybe perfectly understanding combinations. Hopefully you're starting to get a little comfort level with these problems, and hopefully when you get the take-home test you could just do the problems without having to refer to the video, but it'll definitely be here to help you. So I think I just have one last problem to do, and it has to do with the cards, and a more standard card problem in that it has me getting 5 cards dealt to me randomly, and it wants me to get 3 kings and 2 5s. So if you read through the problem, it tells you what a full house in poker is. That almost is more of a distractor. This is the part of the problem that I'm going to use to get my probability. I'm being dealt 5 cards of 52 cards. The denominator I'm going to write for this problem is 52 choose 5 because I can get any 5 of the 52 cards. The numerators, I want to get kings and 2s, so I'm going to make a combination for the kings. I want 3 kings, and I want 2 5s, or 2 5s. So I made a combination for the kings that I want, the 5s that I want. To the left of the combinations, I want 3 of the 4 kings and 2 of the 4 5s. This is going to be a combination that is going to get an E when I do it. I'm going to write my answer with not all zeros. I'm going to clean up my answer. I mean, my answer is going to have a lot of zeros in it and a number to the right of a 0. So in the numerator, the first combination is 4. Second combination is 6. And the denominator is a really big number. It's 2,598,960. So now I'm going to go 4 times 6 in a parentheses divided by 2598960. Enter. I knew to get the E. Math. Enter. Enter. So my calculator tells me this is 9.23446 and a bunch of other stuff. E to the negative 6. I'm going to take the decimal, move it 6 places to the left. So I'll go 1, 2, 3, 4, 5, 6. Fill in these, and move the decimal there, and then fill in a bunch of zeros. And for my answer, I'm not going to write just 3 zeros. So I'm going to write 0.000, 1, 2, 3, 4, 5, 6. I added too many zeros. Should I be 5? So there's 1, 2, 3, 4, 5 zeros. So 5 zeros and a 9. And you could write a 0 to the left of the decimal, but that one's optional. So that would be the answer I'd write for 40 if this was a test question. I think that's all I decided I was going to do from section 1210. So hopefully when you get the take-home test that you can figure out which problems on the take-home test are combination problems, and when you have a combination problem, figure out which ones you need fractions to solve and which ones you don't need fractions to solve. Fractions are probability questions. Non-fractions are how many questions. The take-home test covers what, 12.7, 12.8, 12.9, and 12.10, and 12.9 and 12.10 are where the combinations come in. Hopefully every problem I put on the test fits real nicely with one of the problems on the video so that you can know what you need to do. I believe there's 20 problems on the test worth 2 points each. And of the 20 problems, I think 3 of them are intentionally hard. So hopefully you can get those. They're not supposed to be so hard that most of you shouldn't be able to get them, but there might be 3 problems where you're like, oh, that's crazy, I don't know what he's asking for. You'll have ample time to work on the take-home test. You can ask me questions as you're working on the take-home test, and I'll decide exactly what I won't answer, but you can ask anything, and if I answer it, you win, and if I don't answer it, at least maybe I might point you in a direction to help you get your answer. Okay, so I'll shut this down.